In the previous session, we have discussed what are sequences and what are the limits of sequences. And if a limit exists for a sequence, then the sequence is said to converge to that limit, and otherwise the sequence is said to be divergent. So, we have seen the sequences which are convergent, and we have seen that the limit, if it exists, is unique. Now, in this class, we will be discussing more on sequences, and we can see the first definition. A sequence xn of real numbers is said to be bounded if there exists a real number m greater than 0 such that modulus of xn is less than or equal to m for all n element of n. So, if we could remember, we have seen the definition of a bounded function. So, what was the definition of bounded functions? A function f of x is said to be bounded if there exists some m such that modulus of f of x is less than or equal to m for every x belonging to the domain D. So, this is exactly the same notion that we are discussing in the boundedness of sequence, because in the previous session we have discussed a sequence is nothing but a function defined on the set of all natural numbers. So, exactly the same definition follows here also. We have modulus of xn less than or equal to m for all n belonging to the set of all natural numbers, which happens to be the domain of the sequence. So, we have modulus of xn less than or equal to m, or this sequence do have a lower bound as well as an upper bound, namely negative m as the lower bound and capital M as the upper bound, because we know modulus of xn less than or equal to m is equivalent to writing minus m less than or equal to xn less than or equal to m. So, this was also seen in one of the previous classes. So, negative m acts as the lower bound, capital M acts as the upper bound. So, that is exactly what the definition of bounded sequence says. Now, moving on to the results involved using boundedness, the first important theorem that we have is that a convergent sequence of real numbers is bounded. So, we have seen what is the definition of convergence of a sequence, and using that definition we are going to show that every convergent sequence of real numbers can be considered to be bounded. So, let us see the proof of it. Proof of boundedness theorem, we can say, we are given that sequence xn converges to some number, say x. Let x be the limit of the sequence xn. Then by the definition of convergence, given epsilon greater than 0, there exists some natural number k such that modulus of xn minus x is less than epsilon for every n greater than or equal to k. So, this was the definition of limit of a sequence. So, this is true for any epsilon greater than 0. So, in particular for epsilon equal to 1 also, we can find some natural number k. I am calling the same number k itself because we do not know which natural number it is. So, we are using the same notation here, that does not matter, such that modulus of xn minus x is less than 1 for every n greater than or equal to k. This is 1. So, modulus of xn minus x is less than 1 for every n greater than or equal to k means we can expand this as modulus of xn minus x is less than 1. So, this can be considered for finding what happens to modulus of xn? So, xn, if you take modulus of xn becomes modulus of xn minus x plus x by adding or subtracting the limit x to it, which is less than or equal to mod xn minus x plus mod x by triangle inequality, and that is less than 1 plus mod x. And this is true when if this is less than 1, and when is this less than 1? For every n greater than or equal to k. So, from k onwards, modulus of xn is bounded above by the number 1 plus mod x. So, what is our intention? Our intention is to prove that a converging sequence is bounded. So, we have sequence xn to be convergent to show that sequence xn is bounded. So, this is our ultimate aim. Now, we have a result modulus of xn is less than or equal to 1 plus mod x for every n greater than or equal to k. So, what about the previous terms up to k minus 1? We do not know whether they are bounded or not. So, let us define some number capital M to be the supremum or maximum of mod x1, mod x2, etc. up to mod xk minus 1, because we do not know whether these are included in this, whether these can be included in this list or not, because this holds only for n greater than or equal to k. So, for safer side, what we are doing is we are taking mod x1, mod x2, etc. mod xk minus 1, and for the remaining terms we can just write 1 plus mod x. So, if we could find such an m, definitely this will imply modulus of xn is less than or equal to m for every n, because we have included all the remaining k minus 1 terms here, and for n greater than or equal to k, it is bounded above by 1 plus mod x as well. So, we have mod xn is less than or equal to m for every n. So, this shows that the sequence xn is bounded. So, that is the result. Every convergent sequence of real numbers is bounded. The next theorem says that is regarding the combination of sequences. Till now we were discussing the limit of one particular sequence. Now we are going to combine the sequences. So, if sequence xn and sequence yn are two sequences of real numbers that converge to x and y respectively, then the sum of the two sequences, that means xn plus yn converges to x plus y, xn minus yn converges to x minus y, xn into yn converges to x into y, Cxn converges to C times x, and xn by yn converges to x by y, provided the denominators are non-zeros. So, these are called the algebra of limits. We can discuss one by one. The first one being, we are given xn converges to x and yn converges to y. So, we will be discussing an outline of the proof. So, we have by definition of limit, given epsilon greater than 0, there exists some natural number k1 such that modulus of xn minus x is less than epsilon by 2 for every n greater than or equal to k1, and given epsilon greater than 0, there exists some natural number k2 such that modulus of yn minus y is less than epsilon by 2 for every n greater than or equal to k2. So, what we want to prove is modulus of xn plus yn minus of x plus y is less than epsilon for every n greater than or equal to some number. So, as we have discussed in one of the previous theorems, we can take the maximum of k1 and k2, because both are natural numbers, means either k1 will be larger than k2 or k2 will be k1 will be larger than k2 or k2 will be larger than k1. So, we can take the larger of these two, so that both these results hold. Then applying the triangle inequality, because this can be expanded as modulus of xn minus x plus yn minus y. So, this is less than or equal to mod xn minus x plus mod yn minus y, and that is less than epsilon by 2 plus epsilon by 2 for every n greater than or equal to k, where what is k? Maximum of k1 and k2. So, that is how we prove that modulus of xn plus yn minus of x plus y is less than epsilon. So, that completes the proof of the first part. The proof of xn minus yn is similar, because we know subtraction is just the reversing, or just by taking yn to be negative yn and then adding, we get the same result. So, addition and subtraction is proven by this method. Now, consider the multiplication case, or much more simpler one we will consider first. We have to prove that Cxn converges to Cx. So, consider modulus of Cxn minus Cx, which is equal to mod C into modulus of xn minus x, and because xn converges to x, we can choose epsilon greater than 0 to be some number, say epsilon by mod c greater than 0, because mod c is always positive. So, actually in the definition of limit and all, the choice of epsilon is flexible. We can choose epsilon, so we can adjust the value of epsilon so that it fits our result. So, here we can choose epsilon to be epsilon by mod c, and that is definitely greater than 0. So, there exists a k1 or k belonging to the set of all natural numbers, such that modulus of xn minus x is less than epsilon by mod c for every n greater than or equal to k. Now, why does it follow? Because of the definition of limit, and we are given xn converges to x. So, we can replace c into modulus of c times xn minus x is definitely less than epsilon for every n greater than or equal to k, and that is exactly what is required in the present case or present situation. So, this becomes less than epsilon for every n greater than or equal to k, and hence it satisfies the definition of limits, and so Cxn converges to Cx. Now, consider the case modulus of xn into yn. Consider modulus of xn yn minus xy. Inside this, here we will do a small manipulation. We will insert xn y, adding and subtracting xn y, we will be getting xn y minus xy. Now, this is equal to, from the first two terms we can take mod xn outside. So, we can write this as mod xn into modulus of xn into yn minus y plus y into xn minus x. Now, applying the triangle inequality, this becomes less than or equal to modulus of xn into yn minus y plus modulus of y into xn minus x, and that is less than or equal to, inside the modulus you have a multiple, that is same as mod xn into modulus of yn minus y plus mod y into modulus of xn minus x. Now, this part is exactly same as the previous case, because c was any number greater than 0 or c was any real number. Instead of c you can take y. So, modulus of y times xn minus x, this can be made less than epsilon as we have done in the previous case. And for doing this part, we use the previous result that we have learned, that is, we know sequence xn converges implies sequence xn is bounded. We have seen this result. Therefore, we could find an m such that modulus of xn can be made less than that number capital M. So, we can replace that xn by capital M, so that this will be made less than m times modulus of yn minus y plus modulus of y times modulus of xn minus x. So, as I told you, we can do a small adjustment with epsilon values, so that this can be made less than epsilon by m, 2m for example, and this can be made less than epsilon by 2 times modulus of y, so that modulus of y and m gets cancelled. We will get less than epsilon by 2 plus epsilon by 2, and that can be made less than epsilon. So, we can do such adjustments to prove the result, but remember that it should be logically correct. Modulus of xn is bounded above by m, and that is why we could replace this modulus of xn by m. Otherwise, what could happen? Because here there is a function on n, as we change the values of n, these can be different. So, we have to get rid of such terms depending on n, other than your modulus of xn minus x and modulus of yn minus y. That is why we are doing this technique. So, this can be proved. And the next result that we want to show is, if we have a sequence Zn converging to Z, where Z is not equal to 0 and none of the Zn's are 0, then we can show that the sequence 1 by Zn converges to 1 by Z. Here also we will be doing a slight manipulation, that is, consider say alpha is equal to modulus of Z by 2. So, since it is mod Z, this is definitely greater than 0. Therefore, there exists some natural number k such that modulus of Zn minus Z is less than this alpha. Instead of epsilon, we are taking alpha to be mod Z by 2. Now, this indicates that negative mod Z by 2 is less than negative of modulus of Zn minus Z, which can be made less than mod Zn minus mod Z. This we have already studied. Modulus of b minus a is less than mod a minus mod b, and using this, the first and the last part of this inequality, we will be getting modulus of Z, this is modulus of Z, minus modulus of Z by 2 is less than mod Zn. Now, why we are doing all this, we will see in later session. Therefore, modulus of Z by 2 can be made less than mod Zn, because mod Z minus mod Z by 2 is less than mod Z, n becomes mod Z by 2 is less than mod Zn. Therefore, 1 by mod Zn is less than, when you take the reciprocal, the inequality gets reversed. So, this is less than 2 by mod Z. Now, why do we require such a result? Name it as inequality number 1. Why do we require such a result is because consider modulus of 1 by Zn minus 1 by z. When you take the LCM and simplify, you will be getting Zn minus Z on top divided by mod Zn into mod Z. So, as I told you in the previous case, if you have a term depending on n other than the required terms, we have to get rid of that extra term. That means, we have to get rid of this mod Zn, because that changes as n changes. So, that is why we require this condition number 1. That is why we have started with alpha equal to mod Z by 2. So, using this result here, you can take this as this is less than, strictly less than you will get, this is less than 2 by mod Z square into modulus of Zn minus Z. Now, because Zn converges to Z, we can do a slight manipulation for the value of epsilon, and we will be getting this is less than epsilon for n greater than or equal to k. So, that is how we do the algebra of limits. So, remember that each case has to be done in a particular fashion, so that we will be getting the result accordingly. So, 1 by Zn converges to 1 by y can be generalized to xn by yn converges to x by y. Okay. So, that is regarding algebra of limits. The next important theorem that we have is, if x is equal to a sequence xn is a converging sequence of real numbers, and if xn is greater than or equal to 0 for every n, then we have the limit also to be greater than or equal to 0. Or in other words, what does this theorem say? A sequence of non-negative real numbers cannot converge to a negative real number. So, that means, if the sequence of real numbers is entirely on the positive side of y, then it cannot come to the negative y. So, limit of xn is always greater than or equal to 0. So, the proof is something very similar. So, suppose we have to prove that x is equal to limit of xn is greater than or equal to 0. So, if possible, let us take x is less than 0. Then what happens? Negative x is greater than 0. So, you take epsilon to be negative x, then there exists a k belonging to n such that modulus of xn minus x is less than epsilon for every n greater than or equal to k. In particular, we have minus epsilon less than xn minus x less than epsilon, because this can be written in this form. In particular, we have minus epsilon less than xk minus x is less than epsilon. So, we have taken epsilon to be negative x here. So, you will be getting xk minus x is less than negative x, which shows that xk is less than 0, which is a contradiction, because all our xn's are given to be non-negative. So, why is that contradiction? Because we have assumed like this. So, this is wrong, therefore, x is also greater than or equal to 0. The same theorem can be used to prove this result. That means, if you have two sequences, one of the sequences is less than or equal to every other term of the sequence, the limit is also less than or equal to limit of yn. This result can be used to show that if you have some numbers a and b, a less than or equal to xn less than or equal to b for every natural number, then the limit lies between a and b. Also, we have a result that if xn, yn and zn are three converging sequences, having the result that xn is less than or equal to yn, less than or equal to zn for every n belonging to n, limit of xn is less than or equal to limit of yn is less than or equal to limit of zn. So, this result is known as the squeeze theorem, which says that if you have limit of xn and limit of yn to be the same, then limit of xn and limit of zn to be the same, yn has no other option, yn has to be equal to or has to converge to the same limit as the other two sequences. So, the proof of this squeeze theorem follows from the definition and also from the given result that xn less than or equal to yn less than or equal to zn, and we can see that if the left hand limit and the right hand limit are the same, then the middle limit is also equal to the same thing. So, in today's class we have discussed some of the limit theorems or some of the theorems on limits. We have seen the algebra of limits. We have seen that every bounded sequence, every convergent sequence is bounded, and we have seen how the limits are changed if we are manipulating the sequences, and also we have seen that a sequence of non-negative real numbers cannot converge to a negative real number. So, that is all regarding the theorems on limits. Thank you.